Hello, today we are talking about phase changes and heating curves. These notes can be found in your book on page 16 to 17. So you've seen thermochemical equations. It's our normal chemical equation with that enthalpy value in it. Thermochemical equations can be written for phase changes as well. So these chemical reactions that we see here, we see H2O solid going to H2O liquid going to H2O solid. Both of those are types of phase changes. The enthalpy whenever H2O solid goes to H2O liquid, or for melting 1 mole of water, is positive 6.02 kilojoules per mole. So it requires 6.02 kilojoules to melt 1 mole of water. If we look at that second thermochemical reaction here, it's actually the reverse, where we're freezing water going from liquid to solid. Well, freezing is an exothermic process. 6.02 kilojoules of energy are going to be released. We can see that due to that negative sign there. Whenever we flip the reaction, that's going to change the sign or change the reaction from exothermic to endothermic. In terms of our phase changes, some are endothermic, some are exothermic. We just saw here that freezing was exothermic and melting was endothermic. Endothermic phase changes are going to require more heat. We need more heat to overcome or break the intermolecular forces between the molecules. Solids have the maximum amount of intermolecular forces. Liquids, we've broken some of the IMFs. Gases, we have no IMFs between the particles. They're really, really far apart from each other. We've had to break all those IMFs. So just like ending a bond is endothermic, ending an IMF will be endothermic as well. Those phase changes that would be endothermic would be melting, vaporization, and sublimation, which is when we go from a solid phase directly to a gas phase without passing the liquid phase. So the opposite of all of these phase changes then are exothermic. They are going to be releasing energy as new IMFs or new attractions are formed. Just like making a new bond is exothermic, making a new attraction or a new IMF is exothermic as well. So condensation, freezing, and deposition would be your exothermic phase changes. For any given chemical, we can look at the heating curve. So the heating curve shows us the change in temperature of a substance as we add heat to it. We always start at our solid phase. So this is a heating curve of water. Below 0 degrees Celsius, we're going to have a solid. Well, to increase the temperature of that solid, we would add heat to it. But once we hit 0 degrees Celsius, we're actually going to be melting at that point. Notice that temperature is not changing during that phase change of melting, and there is both a liquid and a solid present. After our solid has completely melted and converted into a liquid, then the heat that we add would go into just increasing the temperature of the liquid until we hit 100 degrees Celsius, which is our boiling point of water. As water is boiling, the temperature does not change. During the boiling process, it stays 100 degrees Celsius the whole time. So whenever you're boiling water on your stove at home, it doesn't just keep getting hotter and hotter. It's going to stay at the same temperature the whole entire time it's boiling and you have that gas to liquid mixture. Once all of your liquid has been converted into a gas, the heat that we're adding again would just go into increasing the temperature of the gas. So as we look at sections 1, 3, and 5 here, these are the points where we are just simply heating the solid, liquid, or gas. That's when our temperature is increasing, we can see from that inclined slanted line there. As temperature is increasing, so is kinetic energy. Kinetic energy and temperature are directly related. but the potential energy is not changing because we are staying in one constant state of matter. So kinetic energy and temperature will be increasing, potential energy staying constant because we have a constant state happening. Potential energy stays constant because IMFs are not changing. Our molecules are just moving faster, aka more kinetic energy. Whenever we look at parts 2 and 4 of this curve, that's where we have the phase change actually happening, and we have that mixture. We have multiple states. So while a piece of ice is melting, there is a solid and a liquid physically present. But again, temperature is not changing during those phase changes. We can see that from our flat lines here. Since temperature is not changing, kinetic energy is not changing either. They are both constant. However, as we go from a solid to a liquid in that melting phase, or a liquid to a gas in the vaporization phase, potential energy is increasing as we break those IMFs. So using our knowledge of heating curves and when our temperature changes are happening versus when our phase changes are happening where temperature stays constant, we can actually calculate the amount of heat energy that is needed to complete a phase change or a temperature change. Again, during those inclined sections, sections 1, 3, and 5, temperature is changing. If temperature is changing, we can use Q equals MCAT to figure out the amount of heat energy it's going to take to change the temperature of that substance. Each of those slanted sections, 1, 3, and 5, would require a separate Q equals MCAT calculation. The specific heat capacity of a solid, a liquid, and a gas of the same substance are not the same. So for example, water has a specific heat capacity for the solid, which is different than the specific heat capacity for liquid, which is different than the gas. Whenever we look at our flat or our plateau sections in sections 2 and 4, one way we can remember those flat plateau sections is our 3 P's. At the plateau is where our phase change is happening, and that's where potential energy change is happening. Remember, during those phase changes, they are flat. There is no change in temperature, which means no change in kinetic energy. To determine the amount of heat energy during that point in time, we're going to be using the enthalpy change for our phase changes, like the enthalpy changes that we saw for those thermochemical equations on the top of page 16. So let's go into a little more detail on calculating these energy changes. So again, whenever that temperature is changing, so we have a single state of matter, temperature is changing, we're using Q equals MCAT. We would be given the grams of our substance. Using Q equals MCAT will give our heat in joules because the specific heat capacity is generally joules per gram degrees Celsius. Sometimes we might see a molar heat capacity. If we see a molar heat capacity, that's the joules per mole Kelvin, so we would need to plug in moles rather than mass to our Q equals MCAT. It would turn into Q equals NCAT. For phase changes, we are using our enthalpy. Whenever we are melting or freezing, we use the enthalpy of fusion. The enthalpy of fusion is the amount of energy required to melt 1 mole. It's positive because melting is an endothermic phase change. Freezing is still the same value for our heat of fusion because it's the same reaction, opposite direction, again, like the thermochemical equations we saw on the top of page 16, but freezing is an exothermic process. Q is negative for an exothermic process, so we put that negative sign in front. N is going to be the moles of our substance because that enthalpy of fusion tells us the number of kilojoules of energy required per 1 single mole. So if we have half a mole, it's going to only take half as much energy. Similarly, we use the heat of vaporization, which is the amount of energy needed to vaporize 1 mole of a substance. When we're looking at that phase change, the opposite phase change, condensing, still has the same magnitude of energy change, but now it is exothermic, so we'll put that negative sign in front to get our negative Q representing an exothermic reaction. N is still the moles of their substance, as the enthalpy of vaporization is given in kilojoules per mole. So using these Q equals Na, so that little formula there, Q equals Na, to help you remember what to do during a phase change. Does temperature change during a phase change? Nah. So we're going to use Q equals Na. So N delta H. We're always going to be starting with moles or solving for moles, and the heat would be given in kilojoules since the enthalpies are in kilojoules per mole. The final step would be to add together the heat of each individual step of the whole process of the heating curve. When we find that whole heat and atom together, we need to make sure we're adding the same units of energy. Generally, part 1 here, that temperature change, Q equals MCAT, is going to give you joules. Whereas the second phase change option gives us kilojoules. So we're going to generally be converting our joules into kilojoules so that we're adding all of our kilojoule values together. So let's start looking at a couple examples of this. We want to determine the amount of heat gained or lost. So gained is a positive Q, lost is a negative Q during the following process. So we're melting titanium at at 1677 degrees Celsius, which would be its melting point. Well, for melting, it's a phase change. Does temperature change during a phase change? Nah. So we're using Q equals Na, N delta H. Well, if we're melting, we need to use the heat of fusion. The heat of fusion for titanium is given to us here, so you might need to add that to your problem. That tells us that it takes 18.8 kilojoules of energy to melt 1 mole of titanium. Well, I have 55.8 grams of titanium. I need to figure out how many moles that is. That's what our Na part of this equation is. That's what the N part of our equation is. To solve for N, which is our moles of titanium, we need to take the mass of titanium that was given to us and divide by the molar mass. Then we just multiply by the heat of fusion. We are melting, and melting is an endothermic process. We do need to keep that heat of fusion positive. That's going to give us an overall energy 21.9 kilojoules gained. So we are melting a little bit more than a mole, so it's going to take a little bit more than the heat of fusion, which tells us how much for 1 mole. Let's take a look at number 2. Again, we want to know the amount of heat gained or lost during this change. We're taking 45 grams of water from 20 degrees Celsius to 115 degrees Celsius. So we have a temperature change happening here, but we're also going to be going through a phase change. We have liquid water at 20 degrees Celsius. It's going to be steam at 115 degrees Celsius. When you encounter a problem that includes both temperature and phase changes, we need to draw ourselves a mini heating curve. Once we have that mini heating curve, we can determine where we're going to start and where we're going to end. From 20 degrees Celsius to 115 degrees Celsius is a part of the heating curve that we're interested in. Each line segment is going to require a different part of the process here. We have 3 separate line segments where the first line segment is heating up our liquid water, the second line segment is the actual vaporization, and the third line segment is the heating of the gas. Again, each of those will require a different mathematical setup. So as we said in that first part of our line segment for the heating curve, we are heating our liquid water. As we heat our liquid water from 20 degrees Celsius to 100 degrees Celsius, anytime we have a constant phase and we just have a temperature change, we're using Q equals MCAT. We can go ahead and plug in our mass and specific heat capacity and calculate that temperature change to find the amount of energy required to heat our water. We do want to make sure that we're using the specific heat capacity of the gas, which is the 2.02. We also want to be paying attention to our sig figs. We only get 3 here. I'm going to keep the full number because I know I have more steps to come using this later, but underline that third or final sig fig. That brings us to part 2, where we are boiling or vaporizing our water. Does temperature change during a phase change? Nah, so we're using Q equals nah here. At N, we'll need to solve for our moles of water. The delta H, we're boiling, so that's the delta H of vaporization. Boiling is endothermic, so we'll keep it positive. Using Q equals nah is going to give us our units in kilojoules due to our heat of vaporization being kilojoules, while Q equals MCAT gave us joules due to that specific heat capacity. Still paying attention to sig figs, I'm going to need to underline the third sig fig, so I only get 3. That brings us to part 3 of our line, where now we're heating our gas. Only have a temperature change. We're just one single phase of matter. That's where we're using Q equals MCAT. You should find that it takes 1363.5 joules. Again, it'll be joules from that specific heat capacity. This time I'm only going to get 2 sig figs because of that temperature change being 15 degrees Celsius. I do have to go and correct myself from earlier. In our first Q equals MCAT heating the liquid, I accidentally wrote the wrong specific heat capacity. That C for the liquid water should be 4.18 joules per gram degree Celsius. However, I was going off my key, so this Q value here is still correct. Once we have the amount of heat energy required for each of our separate steps, we just simply must add them all together. Before we can add them all together, though, they need to be in equivalent units. My 1 and 3 are in joules. I'm going to convert them to kilojoules. Once each step is in kilojoules and we've added them all together, keeping our sig figs in mind, we'll get to go to the ones place following our sig fig rule for addition. Going to the ones place, we'll round to 118 kilojoules for that process of taking our 45 grams of water from 20 degrees to 115 degrees Celsius. So taking a look at number 3, it's similar to examples we've already done. Take a moment, pause the video, and try this out on your own. Resume the video when you're ready to check your answer. So one of the first things we look here, we need to figure out what is happening. We're going from 32 degrees Celsius from 320 degrees Celsius for our solid aluminum. The melting point is 660. So we don't have a phase change happening. It's solid the whole time. It's not going to melt till we get to 660. We're only going up to 320. So we do not need this heat of fusion. Only a temperature change means we're using Q equals MCAT, but the specific heat capacity was given us in joules per mole, so that's actually our molar heat capacity. We need to use Q equals MCAT. Our N, we'll want to solve for our moles of aluminum. We'll use that molar heat capacity and find our temperature change. We get to keep 2 sig figs from our 6.9 as well as that temperature change, so we end up with 67 joules of energy required in this process, so positive Q. Number 4 is another example similar to what we've seen. Take a moment, try that out on your own. This time we're melting aluminum at 660 degrees Celsius, given that heat of fusion and specific heat capacity again. Resume the video when you're ready to check your work. So we only have a phase change happening here. So we're using Q equals nah. It is melting, so we need the heat of fusion, which is exactly what was given to us. The heat of fusion is the amount of energy per 1 mole of aluminum. We have 27.3 grams. That's just barely over a mole of aluminum, so it's going to take barely more energy, giving us 10.9 kilojoules there. Moving on to number 5, it's a little different than the examples we've seen. You can go ahead and pause the video and give it a try on your own. We are talking about water and its boiling point, the heat of vaporization. We're at 25 degrees Celsius and 1.05 atmospheres of pressure. We want to find the volume of water if 620 kilojoules of energy was released. So again, you can give that a thought, try it out, pause the video and resume, or continue on for the deets. So as we look at this, we're going through a phase change. We're vaporizing water. So we're looking at our Q equals Na. We're given the heat of vaporization, which we need since we're vaporizing, and how much energy was released this time. So we're actually given our Q, and we need to know how much water. We're looking for the volume of water. Well, if I find my moles, I'll be able to find the volume. I'll have an amount that I can then work with. So we need to solve for that moles of water. We'll plug in that heat of vaporization there. So that gives us 15.2 moles of water. The other option that we have to do this is using that heat of vaporization as a conversion factor. We have 620 kilojoules of energy, and that enthalpy of vaporization tells us how many kilojoules of energy per 1 mole. So that's 40.7. 620 divided by 40.7 will tell us our moles of water, which would still be 15.2. Okay, so now we have our moles of water. We need to find our volume of water. Well, going from moles to volume, are we at STP? Nope, not at STP. If not at STP, use PV equals nRT. So we'll plug in all of our givens to PV equals nRT, solve for our volume, we're good to go. In terms of our R value, we match that with our pressure unit, so we need to use our atmosphere's R. Temperature must be in Kelvin. With our 3 sig figs that we'll get to keep, we have 354 liters of our gaseous water after it has vaporized. Following this, you have some more heating curve practice on the second half of page 18 and some multiple choice onto page 19. Give those a go. Make sure you got the hang of these calculations.